You know that feeling, right? As a researcher, you're nurturing this massive language model, this digital brain, aiming for really deep understanding. You train it with all the latest stuff like Roki, optimized for these long sequences. And yeah, it nails the short stuff, quick questions, snappy replies, no problem. But then you push it, say 128,000 tokens, maybe even 256,000, and suddenly it's just fumbling.
Right, fumbling. Important details just vanish. Attention wanders off. It's, like you said, trying to find that single grain of sand in a whole desert. It's frustrating.
So then you try something totally different, maybe no P, no positional clues at all, and kind of surprisingly, it finds those needles better in the long stuff.
It does, but then the trade-off hits. It struggles with basic short tasks, like it completely forgot how to tie its own digital shoelaces.
Exactly. And then there's QK norm. That's supposed to smooth things out, make attention stable.
Supposed to. But for long context.
Yeah.
Turns out it makes things even worse than both Rope-E and Nope-E. It's kind of shocking, actually.
So you spend like countless hours staring at code, at charts, pulling your hair out, and then maybe it clicks.
Yeah, the realization that these approaches, Rope-E, Nope-E, they might seem opposite, but they share underlying ideas.
Like what? What are these shared abstractions?
Well, things like how they handle positional clues, how they focus on retrieval versus, say, recency, and just balancing the whole context window.
Okay, so different tools for similar underlying jobs, and that leads to the idea of mixing them.
Precisely. What if you could combine their strengths strategically, layer by layer? A bit of Nope-E for retrieval, some Rope-E there for local stuff, back and forth.
And suddenly maybe your long context model just leaps ahead in performance, while short tasks, they hold steady.
That's the hope. And then you refine it more, maybe add a sliding window to some Rope-E layers.
Sliding window. Like blinders almost.
Kind of. Locks in that local focus for Rope, but lets the Nope-E layers roam free, connecting distant ideas across the whole text.
So 128K, 256K, still finds the needle.
Still finds it. While the baseline Rope-E model, the one you started with, it just crumbles at 256K. But this new hybrid, it stays strong.
And you realize you didn't just tweak Rope-E. You didn't just make no PE work better.
No, you've actually trained long context attention itself. You've taught the model how to pay attention effectively over huge distances.
If someone comes along and says, okay, but it's just an 8 billion parameter model, how good can it really be?
And you point them to the results, to Arno PE SWA. You show how it beats Rope-E scaling, even way out at 256K tokens.
And if they say, oh, but hybrids are just, mixing things together, it's not fundamental.
You show the ablation studies. You show that even mixing in just one layer of the other type transfers benefits. It's not just random mixing, it's structured.
What if they challenge, but it's not real long context, you didn't train it that long?
Then you demonstrate how it generalizes perfectly to 256K, even though it never explicitly saw sequences that long during training. That usually quiets the room.
Yeah. And you realize you didn't just build a better position encoder.
No, you build a bridge.
A bridge between short context smarts, that quick thinking,
And every long sequence, every massive document that will ever need understanding.
Welcome back to The Deep Dive. We're the show that takes complex research like this and, well, it gives you the shortcut to really knowing what's going on. Today, we are definitely embarking on that journey, diving deep into the architecture of large language models, LLMs, specifically how they manage to remember, and I use quotes there, and process these incredibly long texts. We're unpacking a really groundbreaking paper. It's called Rope to Nope and Back Again, a new hybrid attention strategy by Bowen and colleagues. Our mission for this deep dive: to unpack the really clever ways they've combined these seemingly contradictory approaches to create an LLM that's not just smarter at long context, but also remarkably way more efficient. So let's start there. When we talk about context length and LLMs, what are we really getting at? Why is handling, a whole book instead of just a paragraph such a huge challenge?
That's a great starting point. Effectively, context length is the maximum amount of information, like the number of words or tokens an LLM can hold in its working memory at any one time. Think of it as its attention span, right? And as that length grows from paragraphs to chapters to whole books, we hit 3 really big hurdles.
Okay, what are they?
First, just monitoring these extended sequences effectively is incredibly complex. How do you make sure the model isn't just skimming, but actually deeply understanding information that's spread across thousands, maybe tens of thousands of words?
Right, maintaining focus over that distance.
Exactly. Second, the computational resources needed for training just explode. We're talking billions of parameters, massive data sets, huge amounts of compute time, gets astronomically expensive.
Makes sense. And the third?
Third is practicality for deployment. For real-world uses, these models need to be fast, low latency, and memory efficient. They need to run on hardware people actually have, not just supercomputers.
So it really sounds like this constant tightrope walk between making them powerful enough and making them practical enough to actually use.
It absolutely is. And the paper we're looking at today really zooms in on two architectural components that are just crucial for this balancing act.
Which are?
The attention mechanism itself and the positional embeddings. Attention is how the model figures out which words are important in a sequence, what to focus on.
Okay.
And positional embeddings are what tell the model where those words are located relative to each other. Order matters, right? So it needs to know what comes before what and how far apart things are.
Got it. So before this new hybrid approach in the paper, researchers were mainly trying a few different strategies for these positional embeddings. Can you break down ROPE, NOPE, and this other thing, QK norm?
Sure. So ROPE, Rotary Position Embedding, has become super popular lately. It's pretty effective, relatively simple to implement, and it has this neat trick involving a parameter, theta, that you can tweak to help the model sort of stretch its understanding to longer context than it was explicitly trained on. Extrapolation, basically.
Okay, ROPE is popular, then NOPE, no positional embedding.
Right, no PE. It sounds weird, but the idea is the model learns positional information implicitly, just from the sequence data and how the attention mechanism works, without any explicit position tags added to the word embeddings. It's shown some promise, especially for really long context, but the downside is it can sometimes hurt performance on shorter, more standard benchmark tasks.
Interesting trade-off. And QK norm, Query-Key Normalization. Sounds technical.
It is a bit technical. It was mainly introduced to make the training process of these big transformer models more stable. And it's used pretty widely. But, and this is a key finding in this paper, it might actually be hurting the model's ability to handle long context, especially for retrieval tasks. That was a bit of a surprise.
Okay, so with those three, ROPE, NOPE, and QK norm in mind, what happened when these researchers ran their initial experiments? They used 8 billion parameter models, right? What showed up on standard benchmarks versus that needle in a haystack test?
Yeah, their initial findings were really illuminating. On standard benchmarks, things like MMLU for general knowledge or HELLA-SWAG for common sense reasoning, ROPE and QK norm performed pretty similarly. Both did well. No PE, as expected, lagged behind a bit on these shorter general tasks. That fits with what others have found.
Okay, standard stuff looks kind of predictable, but the needle in a haystack, that's the long context test, right?
Exactly. That test is designed specifically to see if a model can find one specific piece of information, the needle buried deep inside a very long document, the haystack. And here, the results flip dramatically for QK norm. ROPE was still the best performer. NOPE actually did decently well, surprisingly well, given its lower general scores.
And QK norm?
QK norm performed the worst, by a noticeable margin. This was a really critical early clue that something about QK norm, despite its stability benefits, was actively interfering with long context retrieval.
Wow. Okay, so that poor performance from QK norm must have made them dig deeper, right? They didn't just look at the final scores.
Absolutely. This is where it gets really interesting. They started analyzing the internal workings, specifically the attention patterns. They measured something called attention mass.
Attention mass, what's that?
It's basically how much focus, how much computational attention the model is putting on different parts of the input sequence. They broke it down. How much attention goes to the beginning tokens, how much to the actual needle itself, how much to the general context around the needle, and how much to the question being asked.
And they cleverly put the needle right in the middle, didn't they? Which is known to be a tough spot.
Exactly. It hits that lost in the middle problem where models sometimes struggle to retrieve info that's neither at the very beginning nor the very end. So what did this attention analysis reveal?
Yeah, what did they see?
Well, first off, all three types, ROPE, NOPE, QK norm, struggled to keep strong attention on the needle as the overall sequence got longer. That's a common challenge, confirms the difficulty. But how they distributed the rest of their attention was really different. Their attention styles varied significantly.
Okay, like how? What did NOPE do?
NOPE layers actually showed the highest attention mass directly on the needle tokens themselves. This suggests it has strong, raw retrieval capabilities, focusing tightly on the target information. They also showed this strong attention sync effect. Right at the beginning of the sequence, they pay a lot of attention to those initial tokens.
Is that good or bad, paying attention to the start?
It can actually be beneficial. Using those first few tokens as an anchor can help stabilize the attention mechanism throughout the rest of the long sequence. So High needle focus, strong beginning anchor for NOP.
Interesting. And Rot-E, how did its attention style differ?
Rot-E showed a really strong recency bias. It heavily preferred focusing its attention on the most recent tokens, the stuff it just read.
Which is good.
Yeah. Great for local context, understanding the sentence right before, keeping track of a conversation flow. But less good for reaching way back into the document to grab that needle from thousands of tokens ago.
Right, prefers recent history. So what about the odd one out, QK norm? Where did its attention go?
QK norm was the real outlier, and not in a good way for this task. It had the lowest attention mass on the needle itself. It also paid minimal attention to those important beginning anchor tokens.
So where was its attention going?
It was kind of dispersed, almost flat, smeared across all the general noisy context surrounding the needle.
Why would it do that?
Well, the normalization process in QK norm essentially squashes the peaks and valleys in the attention distribution. It makes everything look more uniform. This makes it really hard for the model to distinguish the important signal, the needle, from all the background noise, which perfectly explains why it performed so terribly on the long context retrieval task. It couldn't focus.
That makes so much sense. It's literally flattening the landscape so it can't see the peaks. Okay, so armed with these insights, NOP is good at retrieval, but weak short-term. Rot-E has recency bias, good for local stuff. QK norm is just bad for this. They had their aha moment, right? Time to build a hybrid.
Exactly. They thought, okay, let's try combining ROP and NOP. They interleaved the layers and called this initial hybrid RNOPE.
And what happened when they first started mixing them? Was it immediately better?
Well, here's where it got really counterintuitive and led to the next big insight. They found that increasing that ROP theta parameter, the thing that usually helps pure ROP models extrapolate better.
Yeah.
In their hybrid RNOPE model, increasing theta actually hurt its long context ability. It made it worse.
Whoa, okay. That's the opposite of what you'd expect based on Rot-E alone. Why?
Their analysis showed that giving the ROP layers a larger receptive field, which is what increasing theta does, actually introduced more noise into the attention patterns. This static from the ROP layers then disrupted the NOPE layers' ability to do their job to effectively retrieve the needle based on semantic similarity. It was like one part of the brain was shouting too loudly and confusing the other part.
Okay, so simply mixing wasn't enough. They needed to manage the interaction, control the noise. What did this lead them to realize? What were the key takeaways?
Right. Two critical insights emerged. First, yes, combining NOPE and ROP definitely offered complementary advantages. NOPE for the long-range pinpoint retrieval, ROPE for efficient local processing and handling recent information. The potential was there.
And the second insight?
Second, and this was crucial, they realized
Specialization and noise reduction. That makes sense. And this led directly to their final architecture.
Exactly. This led directly to the novel Arno-P-SWA architecture.
Okay, let's break down Arno-P-SWA. What are the key design choices? What did they actually build?
Right. Arno-P-SWA stands for rope NOP with a sliding window attention. It's really quite elegant. First, based on those early results, they completely threw out QK norm. Gone. Too detrimental for long context.
Good call. What next?
Second, they specifically included NOP layers, but crucially, these NOP layers operate with a full attention span. They get to see the entire document, allowing them to handle that long-range retrieval based on vector similarity. No restrictions for NOP.
Okay, NOP gets the global view. What about ROPE?
Third, they applied sliding window attention, SWA, only to the ROPE layers. This gives the ROPE layers a hard limit on how far back they can look, say 4,096 tokens.
So like putting blinders on ROPE?
Pretty much. It forces ROPE to focus on its strength, processing recent local context efficiently, using its recency bias effectively, without getting distracted by or interfering with stuff happening way earlier in the document.
And did they figure out how many of each layer type to use?
They did. They ran ablation studies, testing different combinations, and found an optimal interleaving ratio. It turned out to be about one full attention NOPE layer for every 3 SWA ROPE layers. So 25% NOPE, 75% ROPE with SWA.
Wow, that's specific. So this design, it balances the local focus of ROPE with SWA and the global retrieval of NOPE while also being more efficient.
Exactly, because 75% of the layers are now using sliding window attention, which is computationally much cheaper than full attention, especially on long sequences. It's a brilliant design for both performance and efficiency.
Okay, the design sounds smart. Let's talk results. How did this Arno-P-SWA bridge actually perform compared to a standard ROPE baseline, one that just uses ROPE and tries to scale it with a high theta? Start with the standard shorter benchmarks. Did they lose ground there?
That's the really impressive part. On most standard benchmarks like MMLU, GSMA-K for math reasoning, etc., RNO-PTY was either on par or better than the strong ROP baseline. They even saw some notable gains, like plus 2.0% on MMLU and plus 1.8% on GSM-8K. This is critical.
Why is it so critical?
Because it shows that even though 25% of its layers are no-payee, which historically struggled on short tasks, this interleaved RNO-PP cell-I architecture doesn't suffer that performance drop. It retains strong general capabilities. The hybrid structure works.
Okay, so it doesn't sacrifice short context performance. That's huge. But the real test, the whole point, was long context, right? How did it do on needle in a haystack and that tougher ruler benchmark, especially when pushed beyond the 128K training lengths?
Right, needle in a haystack first. Within the 128K context length they trained on, both RNO-PB SOI and the baseline ROP model did almost perfectly. No surprises there.
But extrapolation, pushing to 256K.
That's where the difference was stark. RNO-PSYI maintained almost no loss in performance, scoring a near-perfect 9.97 out of 10. It extrapolated beautifully. The baseline ROP model, however, even using a high theta value specifically chosen for extrapolation, just failed to extrapolate well.
Right.
Its score dropped significantly, down to 8.25.
Wow, quite a gap. What about the ruler benchmark? You said that one's designed to be even tougher.
It is. Ruler includes more complex long context retrieval and question answering tasks, and it really separated the two models. The baseline ROP model suffered a sharp drop in performance as the context length increased. We're talking about the 44% degradation in its scores, going from 8K tokens up to 256K tokens on retrieval and QA tasks. It just couldn't maintain performance.
Ouch. And RNO-PSY?
RNO-PSY showed remarkable resilience. It still had some drop, which is expected at extreme lengths, but it was only about a 22–23% degradation over the same range. Much, much better. It clearly demonstrated superior long context capability under pressure.
Okay, so significantly better long context performance, especially under extrapolation and on tough benchmarks. But you mentioned efficiency gains earlier. This wasn't just about scores.
Absolutely not. Their practical implications are huge. RNO-PSY achieved a nearly 4x reduction in KV cache size.
Remind us what the KV cache is and why reducing it matters.
The KV cache is essentially the model's short-term memory during generation. It stores intermediate attention calculations, keys and values, so it doesn't have to recompute them constantly. But it gets massive for long sequences, becoming a major memory bottleneck.
So a 4x reduction is enormous for memory usage.
Huge. It means you can run the model with much less RAM or handle much longer sequences with the same amount of RAM. This also directly translates to speed.
How much faster?
Training throughput was about 50% faster at 64K context length and nearly twice as fast at 128K context length.
Wow, double the speed. Why?
Because 75% of its layers are using that computationally cheaper sliding window attention. Less calculation per layer adds up significantly.
And for inference, when actually using the model.
They saw up to a 70% reduction in latency, how long it takes to get an answer, particularly with very long input sequences. That's approaching the theoretical maximum speedup you could expect, which would be 75% based on the layer ratio. It's an incredible leap in practical efficiency.
So better performance, especially at long context and extrapolation, and drastically reduced memory and much faster speeds. It sounds like they really cracked something important here.
They really did. It's a compelling demonstration of smart architectural design paying off.
This paper, it really feels like it could redefine how we approach building LLMs for these extreme context lengths, doesn't it?
I think so. And it adds to a growing body of evidence.
Yeah.
You mentioned other models like Yoko and Jamba 1.5, suggesting that these kinds of carefully designed hybrid attention mechanisms might generally outperform just trying to scale up full attention.
It challenges that old assumption that just more attention everywhere is always the best path. Maybe specialization is key.
It seems that way. The idea of harmonizing different attention strategies, each optimized for a specific role, local versus global, recency versus retrieval, seems incredibly powerful.
It really does feel like they moved beyond just position encoding and trained long context attention itself, building that bridge like we said at the start.
Yeah. And what's also fascinating, and they acknowledge this, is that while they've achieved so much, there's still a bit of a mystery. They highlight that we don't fully understand why these hybrid mechanisms are so superior at a fundamental level.
So there's still more digging to do.
Definitely. It raises important questions for future research. How can we further reduce what they call attention noise across these vast context windows? Can we find even more sophisticated ways to integrate positional information with the context itself while keeping things efficient? There's still a lot to learn.
Absolutely. So, for you, our listener, the next time you see an AI summarize a huge report or answer a question from page 500 of a document, maybe pause and consider the incredible complexity underneath. Think about that intricate dance of ROPE and NOPE, that careful balancing act of local focus versus global retrieval, and the tireless work of researchers building these kinds of bridges to help AI truly understand every single long sequence. What stands out to you from this deep dive today? How do you think these more efficient, long context capable models might change the AI tools you use every day? Something to ponder.